Hi again. This is a pretty important lecture because we're going through a major transition now in the semester. We're going to move from mechanics and bicycles and things that have to do with mechanical systems, flows, all these sort of laws you've learned. And now we're going to step over into the domain of electricity. And that'll be terrifying for some, it'll be reassuring for others, and my job is to get you through that transition in a smooth way and hopefully get you excited about the things you can learn when you're thinking about the body as an electrical system, because it is, of course, a mechanical system, but a great deal of the control is also electric. So we have to understand how electricity works in the body, how we measure it, what it means, and some basic ideas about how we manipulate it and solve problems with it. So we're going to talk about Kirchhoff's laws and circuit analysis today. But before we get into those details, I want to talk about electricity as it arises in the body. I'm going to call it bioelectricity. It's a word that's used very commonly. You can find textbooks on it. And the body is electric. The body generates its own electricity. It all comes down to these ions that you see here. These are the ions that you've heard about before. We discussed them in the context of diffusion. And guess what? They're going to come back again, and because they're charged, they will be the charge carriers that we'll be talking and thinking about a lot. We will not talk about electrons very much, unlike many other applications of electricity, because in the body, electrons are not the charge carriers. Their charge carriers are the ions. Now, there are many sources in the body of electricity, and the heart is a major one for sure. We call these cardiac sources. The source of electricity here goes right down to the cell. Each cell generates electricity. We will cover that later. And then this collection of cells create not massive, but macroscopic electricity that we can measure in the body surface. And that's the ECG, which you've all heard of, or EKG, it's the same thing. And so the image you see here are individual time signals from different parts of the heart, from single cells within different parts of the heart. And then all those, 10 billion or so cells get together in some carefully coordinated and complex way and produce a signal at the bottom, which is schematically like what you'd see if you put electrodes on the surface of your thorax. So that's the electricity that comes from the heart. And we can talk lots about that, trust me. But muscles also generate electricity, again, because ions are moving around. And there are signals we can record. We can place electrodes on top of the skin near muscles and actually record signals like this that really characterize and show the time course and the amplitude of muscular contraction. Of course, another kind of minor source of electricity, you could argue, is the brain, of course. And so because I'm a heart guy, I have to make fun of the brain a little bit, but obviously the brain has enormous function, enormous importance, the whole nervous system, and all elements of the nervous system involve electricity. They involve chemicals and lots of other things, but there's electricity that comes from our brain, which we can measure on our scalp, and that's called an electroencephalogram, or an EEG. There are even magnetic fields that both the heart and the brain generate, and they can be measured. They're very small, a millionth of the Earth magnetic field, but we have the technology to measure those as well. So there's a lot of electricity going on in all these organs, in all these systems, and our job today is to try and understand a little bit about that, but probably first we're going to spend some time on fundamentals of electricity, a little more generically. So these type of ions that you may read about, positive ions, negative ions, they have to be in balance. One is good for you, one is bad for you. This is all hocus pocus. This is not physics. This is not even good biology. So forget about all those kind of ions that you may worry about, and don't buy an ion generator for your home. It really doesn't do any good. There's no science behind any of this. So let's get back to science. Now, the science you should know, probably very well by now, because we've even slipped under the door a little bit for you, is the science characterized by what we call Ohm's law, which clearly you've had before in physics. There are different ways to write it. There are many ways to use it. This will be the law that will dictate a great deal of what we do for the rest of the semester. And just as with other laws that have this form, we'll ask questions about its linearity, what it depends on. We'll manipulate it and flip it. We'll talk about it in terms of a driver and an enabler. In this case, the driver is, guess what? The voltage difference parallel or analogous to the pressure difference that we saw earlier when we were thinking about flow and the driver in flow. The enabler here is the conductor, and the value we can attach to that substance that conducts electricity is conductance, of course, which is 1 over the resistance. And we'll play with these units, see there's lots of different ways. So this should be totally familiar. I don't need to spend a lot of time on it now, except to say that there's a few basic things that one can observe out of this. Just as the case with flow, if there's no driver, no voltage difference, there is no current. And if the conductance is also 0, just like there's no enabler in a flow situation, then we have no current either. And so we have to have both these things in order for there to be flow, and we have this lovely, simple mathematical relationship that captures all this behavior. And again, we'll be using it again and again. So Ohm's law, we can already see from the function, or from the shape of it here, from this mathematical expression, is a linear relationship, just like all these other linear relationships we've talked about, or apparently linear relationships. Of course, it's nonlinear in lots of situations, and we'll describe some of those even today. It's not a universal truth, but it's remarkably common across electricity, with a few adaptations to deal with that nonlinearity aspect of it. And again, we'll see that shortly. And as with all equations we apply to the body and all models we derive from those equations, it's not perfect, but it's good enough to be actually quite useful to understand behavior. So we'll use it, maybe abuse it, and it will help us a lot in understanding the electrical behavior of the body of lots of other systems. Now, fundamental to all electricity in the body, outside the body, is this notion of a conductor and its opposite partner, a resistor. So what are conductors and resistors generically? They're pretty easy to understand in some regards, but pretty subtle in others, and we'll keep at the easy level of that spectrum. But perfect conductors, and again, we'll do this a lot. We'll talk about perfect things, and then we'll add in a little bit of reality to make them actually useful concepts. So a perfect conductor has complete movement of charge inside it. The charge is free to move around, redistribute itself as needed in order to reduce all of the voltage differences that arise within that piece of material. So there's block here, this orange block. That's, let's pretend, a perfect conductor. So there are charges. You can see there's some negative charges. They might be electrons. They might be negatively charged ions. It doesn't matter. They are free to move around. And that's an important feature here. So as they're free to move around, and they will move around in such a way to reduce all the voltage differences. So wherever there's a voltage difference, it might arise a little micro voltage difference, a little bit of current flows to balance that out until that charge in there is distributed uniformly and there's no voltage difference within that area. And as we'll see eventually, and you may already have some intuition for this from physics, where there's no voltage gradient, no differences in voltage, we have no electric field. Now this doesn't mean voltage is 0. So voltage does not have to be 0 for this to be a perfectly legal conductor. In fact, we can apply a voltage to this whole object and have it at some higher voltage than 0. We could get a shock if we touched it, but within the material itself, there is no voltage difference. There is no current flowing. When we touch it, then we create a more complex circuit that allows current to flow. But as it's established and sort of in its own equilibrium, there is no current that flows inside a conductor, perfect conductor. Only when we attach it to something, make it part of a circuit, like I say. So that's a conductor, a perfect conductor. Now, a resistor, of course, is the opposite. So a resistor is a material where the charge is, guess what, not free to move, where there are internal voltage differences. In fact, as you know, at a discrete resistor, you have one voltage at one end and another voltage at the other, and what we call a voltage drop in between the two ends of that resistor, that discrete element. Just as with other characteristics of material, which is what conductance and resistance is, we can write down an equation. This is one of many equations we can write that says the resistance is a function of resistivity, and that's that rho value. That's a characteristic of the material that the object's made of. And then, without too much imagination, we can imagine that if the object is longer, it's going to have more resistance. And it turns out it's a roughly linear relationship. So the L goes in the numerator. And we can also imagine that as the object has a bigger cross-section, it's going to have less resistance. And sure enough, that's true. Again, roughly linear relationship. So we get resistance is equal to rho times L over A. And that's a simple relationship that we'll also use sometimes to move between resistivity of a material, which is a constant you can look up, and the resistance of an object that has a certain shape, size, dimensions. And as long as it's cylindrical, we can use this simple formula and even predict with reasonable accuracy, again, what the resistance of an object will be given certain resistivity and size parameters. So it's very useful to actually work with. Now, we have conductors like this, and you can say, what does that have to do with the body? That's not how the body works. Well, it doesn't. So the body is also a conductor. It's not a perfect conductor. It has resistive elements in it, but it has conductance, in part because we're sort of an electrolyte soup, and electrolytes are ions, and that means there's charge carriers, and they're somewhat free to move. And so we have the conditions that sound like a conductor, and indeed we do conduct. And in fact, when you think of a piece of us, a volume of us, we call it a volume conductor in the world of sort of bioelectricity. So that's another term you may come across. But let's keep it simple for this. At this point, let's imagine a two-dimensional slice through a piece of tissue. There are cells inside there. They're, again, very schematically circular. So there's a light blue here, that electrolyte, right? Electrolyte solutions are always light blue. Of course they're not, but we have an electrolyte solution and cells sitting immersed inside it, and we apply electricity across that piece of material, here rendered in two dimensions. And the question is, what's going to happen? And on the right-hand side, we see sort of a schematic of the same thing. And that's what we want to be able to move to. This is what allows us to do calculations. If we look at that blob of blue with some red cells floating around it, we can't do too much with that. But that picture on the right, we can do a lot with that. We recognize those as resistors and capacitor, and we can write circuit equations that describe that behavior. So that's what we want to do, is move between the left-hand picture, which is the physical reality or the anatomical or functional reality, to the right-hand side, which is the schematic rendering of that reality. And that's always where we're headed as engineers, because that allows us to solve actual problems and put numbers behind it. So anyway, what happens here? So we apply an electric field, a voltage across those plates that are sitting above and below that object. Current will flow between them, of course. And you can see there's some dimensions there. They're not so important for us right now. So you can imagine, you can hypothesize that when I turn that electricity on, current will flow from the top to the bottom, just like I have it rendered there. And if this were just an electrolyte soup, it might actually work out that way. But we don't. We have a composition of the electrolyte soup and objects inside it called cells. And we need to know more about those cells before we can predict what will actually happen. We have to know what the relative resistance is of these cells compared to the electrolyte. And it turns out cells are surrounded by a bilipid layer. You hopefully maybe remember that from early in the semester, and we'll even play that video again. And that bilipid layer, like all lipids, is a pretty good insulator. So it doesn't let electricity, charged particles, flow through it very well. So the cells actually are pretty good insulators, or they're surrounded by good insulators. Inside the cell, there's also a resistance. But if we can't get past that membrane, it's like each one of these is, surrounded with a little rubber coating or something that, as you know, doesn't let electricity through it. So the picture wouldn't look like this. It would look something more like this, where the current is moving around those cells, taking a tortuous path. It's still going from top to bottom, but not through the same simple path that we might have if there were no cells. And this is the kind of thinking that we have to go through to predict how current flows in the body. And yes, it makes it complicated. I can't apologize for that, just the way it is. But at the end of the day, we still have ways to do that. We have ways to capture that. We have ways to assign resistivity to the different elements and figure out the bulk conductivity and resistivity, those pieces of tissue, even in 3 dimensions. And we do that. That's part of our trade, if you will, when we work in this area of bioelectricity. So we can do that. And we're not going to have to worry too much about it. We're just going to work under the assumption that it's possible. We can do it. Because we're going to use the right-hand pictures a lot more often, the schematic pictures with resistors and capacitors and a power supply, and that's what we're going to talk about a lot more now. And that's what we're going to build our circuits out of and try and solve those circuits. So, next little mini chapter is about resistivity or resistors and how they connect. just as you've already learned for flow, we can have serial connections of resistors. We can have parallel connections of resistors. All of this stuff you can completely carry over from mechanics because we've built up that knowledge already. I don't even want to talk much more about it here. You'll get a chance to practice this with some homework assignments to make sure you know how this works. But the rules are there. You've seen all this before. I won't spend time on it. Something that you may not recall, although we did do some things like this, is you can create curves that characterize the behavior of electrical elements. And we did this a little bit when we characterized pieces of vessel, for example, and we had curves of flow versus pressure. You hopefully remember those. And we can do the same thing here, only we replace flow of a liquid with current flow, and we replace pressure, of course, with voltage. And that gives us what's known as an IV curve, or a current voltage curve, or current voltage relationship. And it turns out this is a little bit like a signature of the behavior of an electrical element. And we can build simple circuits like you see here with a resistor. That's what we're going to be testing. That's our object that we want to characterize. We have V is a voltage sensing device, a voltmeter. A is a current sensing device, an ammeter. And the thing on the right is the symbol we use for a voltage power supply. So we can also adjust it. That's what the arrow means. So we can build this in the lab. It's very simple. Voltmeter, ammeter, power supply that we can control, whatever our test object is. If we put a resistor in there in that test object, that would be like in the mechanical context, like putting a vessel inside a system with an applied voltage and a certain amount of resistance that we're trying to test in this vessel. And then we measure the current. And we did this. We did this at least conceptually. And so we have some idea what came out of that. And what came out of that for, let's say, simple Poiseuille's law of flow is a straight line, right? So we should expect a straight line here. And sure enough, that's what should come out if this is really a resistor. So we can adjust the voltage, different values, record the associated current. In this case, we have both positive and negative values. Voltage can change polarity, and with that, the current direction will also change. But we get a straight line. And we also know, what do we care about when we have a straight line? We care about the slope, and we care about the intercept. So in this simple circuit, the intercept goes through 0, and the slope is what? Well, the slope is current over voltage. And current over voltage is the same as conductance, G, 1 over resistance. This is just like what we saw in this situation with flow. Should feel familiar. And if it doesn't, go back and look at that other stuff, because you got to know this. So that's the simple current voltage characteristic of a resistor. Life is good. So now we move to something you've also come across in the mechanical context, and there it was in the disguise of a valve. And what do we call the electrical component, the electrical element, the analogous piece to a valve? We called it a diode. That's because that's what it's called. So a diode has a different characteristic, but we can also characterize it using this current voltage relationship, just like we did with a resistor. We can build it into a circuit, replace the resistor with now a resistor and a diode in series. And there's some subtlety as to why the resistor has to hang out there. It's actually to protect the diode from burning up. So it limits the amount of current that this thing will actually allow to pass through, because we know, like a valve, a diode allows current to pass in one direction but not in the other. And so we can already imagine what kind of shape a curve like this would have. Now, it's not a square function. It's not, although you could recognize it or realize it, better said, in your computer code with an if statement, just like you've done already with valves. It has sort of, generically that shape. But a diode has, if you look carefully enough, has a little more subtlety to its shape than that. But we can still characterize that relationship. We can measure it in the lab when we get a curve that looks something like this, which is obviously an exponential curve. We can come up with an equation like this that describes that behavior. And it is pretty close to an on-off switch, but it has controls. You can determine when it turns on, when it turns off. There are lots of subtle things about a diode that make it, in some regards, way more versatile than many valves. And so we can look at that curve, that red curve, and say, okay, what does that tell us? It tells us that It's not a linear function, or at least not linear throughout. Remember, we looked at functions before and we said this is piecewise linear. Here, the bottom is piecewise one part, and then further along as you go to the right with voltage, there's another part that is piecewise linear, and in between is this exponential transition. Now, even though it's changing shape, it has a slope. The slope just is not constant. So we can picture a tangent line at any point on that curve, figure out what the slope is there. And that slope, again, is current over voltage, which, of course, is conductance. So we can actually, from a curve like this, extract the conductance values if we know the function itself, if we know the way current and voltage rely or relate to each other. We can determine the conductance, and the conductance will not be a constant. It will be a function of, let's say, voltage. So as the voltage changes, the slope changes, and that means the conductance changes, and that describes the diode. So that's the diode. So those are the elements we're going to work with throughout the rest of this part of the course, and you can do a lot with those. We're going to add in capacitors in a little bit, don't worry. That will come back. Compliance is still very much realized in electrical terms too. But let's live in the world of just resistors to start with, because we have some higher order things to think about first that are going to help us solve circuits. And there's two laws, Kirchhoff laws, you've heard of these before. And I want to put them in a simple context because they really are simple, just like they were in the equivalent laws when it came to flow. They're conservation laws. Physics is full of conservation laws, and this is another one. And you can imagine that we have, just like we have in the mechanical setting, conservation of energy. Just like we had in the mechanical setting, conservation of current flow. And sure enough, that's the case. So the first one we're going to talk about is the conservation of energy. Now, energy or work is definitely very closely related to things like pressure changes. That's another form we can use to think about energy. When something has a pressure in one direction, then that's sort of downhill direction in terms of energy. The same is true with voltage across resistors. And so we can use conservation to say that the sum of the voltages around any loop has to be zero. Sum of the voltages around any loop has to be zero. The power supply, the Vs on the left, generates the power. It's the source of potential energy. And then the current flows downhill from there, achieving something vaguely like kinetic energy. Oh, that's not maybe a perfect analog, but it certainly generates current flow. So we have the power supply, and across each one of those resistors, there's a little drop in voltage. And if you add up all those drops, V1, V2, V3, that has to equal, or together with Vs, is equal to zero. Now you notice there's a sign change here, and this is fundamentally important. We'll come back to this in the context of Kirchhoff's laws. We have to keep track of signs, just like we did with pressure, right? Higher pressure, lower pressure. There's a change in pressure, but we have to know which end is the higher of the two values. Same thing with voltage. So we have to know that here, for example, because the power supply or the battery is oriented the way it is, with a positive terminal at the top, then the current will flow clockwise. And when it flows clockwise, that means that the voltage drops from a positive to more positive to a less positive, or positive to negative relative value across each one of those resistors. And that sign convention is something we'll talk about again and again until you get it straight. So that's conservation of energy. Now we have conservation of flow. This should look totally familiar. Same thing we talked about and used in solving the systems of flow in the body. And it simply says that in this case, the sum of all the current flowing into a node has to be equal to zero. Again, that's nothing new. You've seen all this before. We don't have to belabor it. We're just going to use it in the context of Kirchhoff's laws. So, Kirchhoff's law. For the conservation of energy, we have a Kirchhoff's law that says when using the Kirchhoff voltage loop, KVL, around a loop, the sign of the voltage contribution across any element is the sign first encountered in the direction of the tour. What does all that mean? So, when we're doing solutions, we're building solutions to problems, then we will do tours, they're called. They're Kirchhoff's tours. And when we do a Kirchhoff's tour, we have to keep track of the polarity of the voltage. And this tells us how we do that. So the way we apply this is when we assume a current flow, in this case clockwise, okay, because the voltage supply, the Vs, has the positive terminal at the top, we're going to sensibly enough assume a flow in a clockwise direction. We don't have to assume that. All we have to do is be consistent, just like with the flow situation. We have to be consistent. So I'm saying with that power supply, I'm going to guess the voltage is going to go clockwise. And now I follow that around, and in that direction, the first resistor I encounter, that V1 drop, which is connected to an R1 resistance, that gets a positive charge, and the other end gets a negative charge. And then I go to the next resistor, and that gets a positive charge as I enter the resistor, and a negative charge as I leave. And those charges tell us how the voltage will drop. So they tell us that the voltage drops from left to right, or from top to bottom, depending on which resistor here. And it's determined by this assumption we make of a current flow in a certain direction. We could draw this diagram the other way. We could assume the current flows the other way. And we would probably come up with a negative value for the current flow. And that's fine. Just like we could have negative values when we figured out flows through vessels. So it shouldn't worry us. It's just a convention that we have to keep because it keeps our signs straight. And it's what allows us to say, okay, now with those pluses and minuses as they are, as we go around the loop, we take the first voltage, V1, and we say that's a positive voltage because I encounter a positive sign as I enter the resistor. Positive V2, positive V3. But what happens when I get to Vs? When I enter the Vs, the battery, the negative end is what I see first. It gets a negative sign. The equation I write for my Kirchhoff's tour is V1 plus V2 plus V3 minus Vs equals 0. If you can get that straight right now, you will save yourself enormous amounts of pain in this class and other classes that involve circuits. Because this is, at least when we use Kirchhoff's laws, this is so fundamental and arguably straightforward, but it's amazing how people get it messed up. Just like you probably at one point got a little messed up with all those flows and pressures and how do I assign the signs. But if you just stick to this convention, you won't go wrong. So please take note of it. Please make sure you apply it, and I'll show you in problems how we actually use it in figuring out what the current is in a circuit like this. So that's the rule number one that we're going to use again and again. So rule two says, when using the Kirchhoff current loops at a node, all incoming currents get one sign and all outgoing currents get the other. This will make things simpler to keep your current straight, to know where your arrows are relative to each other, and how to assign the appropriate signs to those. It's not complicated. Again, it's one of those things, if you stick to it, you'll make fewer mistakes and life will be happy. So here we see I1, I2, they're flowing into the node, they get a positive sign. I3 is flowing out of the node, it gets a negative sign. And this is how we orient things. You see at the node in the bottom, we're assuming that I3 goes in and I1 and 2 go out, right? Because I3 came in through the top, goes through the resistor, continues down to the bottom, it's going to flow into that node at the bottom. The other currents, I1 and I2, are going to flow out. So they get the same sign because they're both outgoing, whereas the incoming one gets a different sign. And that allows us to write this simple and hopefully logical equation. If you sort of think about it for a second and say, well, the sum of the currents going into that node are going to equal the current leaving the node. I1 plus I2 is going to equal I3. So these are sensible and logical, not weird and irrational. And if you stick with them, you'll tend to make fewer mistakes. And there are lots of places to make mistakes in these kind of problems. So what are we going to do with this? And how are we going to use our Kirchhoff's laws? The textbook has some nice examples. Please read the textbook about Kirchhoff's laws, how they work. And we're actually going to go through, in a subsequent video, we're going to go through an example, step by step, to show you how I think you should lay out your homework assignments, your midterms, whenever you solve a problem like this. This is the problem we're going to deal with. This is the problem that comes out of your textbook. You can see there's these KTs, those are Kirchhoff tours. You can see there's nodes, node 1 and node 2. So that already gives us a place to start thinking about these tours we're going to make where we keep track of the voltage. We have current directions assigned here so we can keep the signs of those straight. I1 and I2 flow into that top node. I3 flows out of that top node. So this is a perfect application for what we just saw a second ago. And we're going to solve this together in the program, in the video I'm going to show you or have available for you in just a sec. So stay tuned. That video will help you walk through these things, and then the homework assignments will really help you practice this in different configurations. So before I go, I have to sort of finish the story that I started a long time ago, and that's this relationship between electrical and mechanical terms concepts. We've been using it throughout this lecture. Here's a formal table that gathers it all together, even with some equations. So at the top you see all the quantities of interest. So on the mechanical side we have things like pressure and volume and flow and viscosity. And on the right hand side are the electrical terms like voltage, current, resistivity, and charge. Remember, charge is like volume. So we have these parallel situations and equations even that describe what we're doing here. So we have on the right Ohm's law, which you've seen before at the top, and that's the resistance relationship. But we had resistance in the context of flow, where it was a change in pressure over flow. And below that we have the equations that we can use for a certain geometry under certain assumptions to describe resistivity to flow on the left, and resistance to flow of electrical current on the right. So you can see those things like the viscosity are similar, in at least analogous in concept, to what we would call resistivity of a material. So these parallels are very useful. The one we're going to get to soon is the relationship between compliance and capacitance. We've already talked about this a little bit, and I'll spend some time talking about capacitance. But again, there are equations that we can use to describe these relationships that we'll come back to. And when you look at those, you'll again see the analogous structure that they have, where we say compliance is equal to a change in volume over pressure, or change in pressure. And here we have capacitance is a change in charge over change in voltage. So the V's here, don't confuse those. The V on the left is volume, the V on the right is voltage. And the textbook tries, with mostly success, I think, to use a small v for the voltage so we don't get confused between the two. But you'll know from the context what is meant, I'm pretty sure. And the third element, which we've talked about already today, is a valve being similar to a diode, and there being, on the left-hand side, this kind of if P greater than whatever, kind of relationship that we saw implemented in MATLAB. For a diode, we have, as I said, a little more mathematical relationship with this exponential function that describes the current as a result of voltage in a diode. So the last concept, the last topic really I want to cover quickly is electric sources. We'll come back to this, I think, in some discussion groups. There are a number of different electrical sources that we kind of have to know the behaviors of. The one you're probably most familiar with is called an independent voltage source. So what's it independent of? Well, it's independent of virtually anything in an ideal source. That means that your little battery that you have, your 1.5 volt AA battery, AAA doesn't matter, whatever size it is, that's a little battery that has a constant voltage, in a perfect battery, a constant voltage, and that voltage will stay at 1.5 until it dies. A perfect battery will stay at 1.5 and then die suddenly, and the chemical energy will be used up, and at that point there'll be no more voltage available for it. That's a perfect source. So that's an ideal one. So a constant voltage across the terminals, and it turns out we can also think about it as having no internal resistance. So if this is part of a circuit like it was in that example, then the current will flow through it with no resistive losses. That's a perfect independent voltage source. Now, we can make this a little more real, at least, by saying, well, we always have a little bit of resistance. This idea of zero resistance, I mean, when did you ever believe in zero resistance? I mean, it's not quite as bad as Santa Claus, but it's possible physically, but it's a really difficult thing to achieve. And so more often than not, by far, we have situations where there is some resistance. And so we change the schematic diagram. We say, well, let's pretend that a real source is like a perfect source connected to a resistance, which we hope is small. That's the internal resistance for that source. And then we just put that little circuit in to replace our perfect battery, our perfect voltage supply, and we got something we can actually use and have a little more confidence that it's realistic. So there's times when we use the ideal source, there's times when we won't. It really, as with all these things, depends on how much complexity we need to answer a particular question. Now there are voltage sources and there are, of course, current sources, and this is also an independent current source. So you can imagine if it's an independent current source, then it will always generate the same amount of current, just like an independent voltage supply generated the same voltage. So here we have a source that makes constant current. Its resistance, though, maybe this should make some sense or be intuitively obvious, its resistance is the opposite. It has infinite resistance. So it does not allow current to flow through it. It injects current into something else if it's connected to something else, but doesn't absorb any current from the rest of that circuit. So again, we have ideal sources, then we have real ones. And of course, internal resistance of infinity, again, when did you last see infinity? So infinity doesn't make any sense. So if we attach an internal resistor across the terminals like this in parallel with the current source, then we have a more realistic current source. And of course, we want to make Ri be as large as possible this time, where the other Ri was meant to be as small as possible. So that this combination still has very high resistance, just not infinite resistance, right? So those are realistic sources, and we're going to see lots of circuits that we can distill down into something like a source on one side and what we'll call a load on the other. So schematically, it looks really simply like this. We have on the left a source, on the right a load. You can picture this as lots of things. You can picture this on the left is your battery and on the right is your iPhone. Or on the left is your amplifier and on the right is your speaker. So this generic diagram, we'll use again and again for different purposes. This is the one we would use with a voltage source. This is the one we would use if we had a current source. So again, we took those real current sources, connected them to a load, and then we try and predict what will happen. So we'll have these two different sources, which kind of mark out the extremes of what unfortunately is a continuum. So it's often difficult in a real circuit to clearly say, is this a voltage source or a current source? Because it could live a little bit in between. I know that gets murky, and we'll leave that subtlety for courses in electrical engineering. You won't need to worry too much about that. So we'll typically work with one or the other type of source and deal with how it functions and keep things a little bit simple. We will add one complexity though, because it's important. So we said independent sources, independent voltage, independent current. What about controlled sources, where the output is dependent on something else, where I can turn up the voltage or turn up the current? You can think that would be a very sensible and natural way to think about where electricity comes from. When you have a real power supply with a knob on the front, then that power supply allows you to adjust the voltage or the current that you want to generate. And so here we have schematic terms for these. These come right out of your textbook. And we have an output that could be a voltage output, the two on the left, or a current output, the two on the right. And it could be controlled by current or by voltage. So we have four kind of different options, and hence four different symbols. And you look carefully at the symbols, you'll see that the plus minus says it's a voltage source, and then the P or Q times some other number, that tells you what's controlling things. So when you see P times I controlling the output voltage of that leftmost source, then that says it's a current-controlled voltage source. And we won't use all of these, but it turns out a couple of them are really important for some of the problems we're going to solve. So finally, as we say, we use these analogs again and again, and I want to use it one more time to say those sources that we just talked about also have mechanical analogies. And we have on the left fluid, on the right electrical. So we can say on the right-hand side, let's say we have an independent voltage source flowing into a resistive load. On the left, we have the fluent equivalent, which is a constant pressure pump, right? Constant voltage, same as constant pressure, and it's flowing into some tube narrowing, which has an increase in resistance, which acts like the electrical resistor. Now, of course, we can do the same thing with current. So the bottom right corner has a current source, electrical current source, flowing through a resistor. And on the left-hand side, here you see not a constant pressure pump, but a constant flow pump, also going through a tube narrowing that acts like a resistor. So we'll spend some time talking about these sources, kind of a useful way to think about where electricity comes from, because, different parts of the body generate electricity, bioelectricity in different ways, and it's sometimes useful to think of them as current sources, sometimes as voltage sources. So we have to have a little bit of that jargon at least clear in our heads. So that's easily enough to get you into this area, this bioelectricity area. Again, it's a transition. You may need to watch this a couple of times. You'll certainly need to look through the chapter carefully. And then we'll come back shortly with a video in which we actually solve some problems based on these Kirchhoff tours and how we apply them in initially fairly simple circuits to get a feeling for how we set these questions up and how we solve electrical circuits. So thanks for your attention. We'll see you soon. Bye for now.